All right, this is a reminder. Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate. Please don't share personal information during class for your own security reasons. All right, so our question was, when you drop a bowling ball and a feather at the same time, which one hits the ground first and why? And it looks like overwhelmingly we are saying bowling ball, right? I'm seeing lots and lots of bowling ball, bowling ball. We're saying it has more mass, gravity pulls it harder. Yes, bowling ball is heavy, the feather is lighter, more weight for the bowling ball, more mass, gravitational pull. Awesome. All right, so it looks like we all are thinking along the same ideas. So let's go ahead and get started and think about, we're going to learn today which one will hit the ground first, all right, which again might seem obvious to you, but it's a really important concept in our class today. So at this point, make sure you have your attendance check open. Give me a green check. I need green checks from Alejandra, David M., Estella, Jelly, and Jackie, Jaden, Taja, green checks. Once we have our attendance check open, the start of class word is under the link in the chat box, so make sure you fill that out. Here's my contact information. We're on day 13 out of 45, and today we are talking about gravity and motion. Please note, yesterday there were some tech issues, so I was unable to upload your assignment for yesterday along with the recording. So we've moved today's stuff forward a little bit. So gravity and motion today, forces and vectors tomorrow, and we'll actually do the lab report on Monday, and after that we'll be back to our normal schedule. Smiley faces, everyone, if that makes sense. Smiley faces, if that makes sense. That should be nice as well, because that means we get to actually do the lab report together in class. Excellent. Okay. Remember, especially my new students, if you are new with us, please remember that the most important area of my course is actually the grades tab, because there are links to everything in your grades tab for the recordings, assignments, and the recordings do have all of the answers for notes. They have all of the steps for lab reports, and they go over every question for the exams. So this is the most important area. I do know that there have been some issues with the videos this year. I think I figured out the problem, so let me know if you're still having issues seeing the videos, but at this point they should be working for everybody. I checked a lot of people's to make sure that they're working. So this is the easiest way to be successful, is to attend every day or watch the recordings on days we don't have class, because attendance is 10% of your grade and we do everything in class. So at this point, here's your grade breakdown. If you started with us on time at the beginning of quarter one, you'll see that your 1D lab and 2F exam are now past due. Together, they make up 60% of your grade. So if you haven't done one of them, your grade is going to be much lower, or if you haven't done either of them, you cannot be passing my class yet. So please make sure you get both of these done. These are the two most important assignments. If you just started on Monday, eventually this is what your grade breakdown will look like as well. You'll have a 60% for labs and exams. Star 360 and attendance are each worth 10%, and your notes, which we do in class, I give you all the answers as we go through class, are worth 20%. So we started talking about Unit 3 applications of forces on Tuesday's recording. Give me a thumbs up if you were able to take a look at that. Smiley faces if you remember talking about friction, gravity, beginning to take a look at that. Let me know. Awesome. Thank you, Vanessa. Thank you, Michelle. Thank you, Hannah. Excellent. All right. So we are going to keep on talking about gravity today. We're going to talk about mass versus weight. Okay, Ari, not a problem. I do have support on tomorrow at 8:30. So I can invite you to that and I can go ahead and help you out with that. Okay. All right, so we are going to learn, we're going to review today how to differentiate between mass and weight, and we're going to talk about Newton's 3 laws of motion again, which you've already learned. We had an entire unit on it, but this time we're going to apply them to gravity. So we're going to take a look at projectile motion and gravity. We're going to take a look at free fall and gravity, and we're also going to look at the gravity between the Earth and the Moon, all based on Newton's 3 laws. So that's where we're going today. All right, so at this point, I do need you to open up your notes. All right, so you're going to have 2 tabs open. All right, and if for some reason your computer doesn't like that, what you can do is you can close your attendance once you have your answer to your attendance for number 1 filled out, and that'll be saved. So if you want, you can just have your notes open, or you can take pictures or screenshots of your notes and just do them after class if that's easier for you, easier to focus if you're not a fast typer, for example. Okay, go ahead, give me a applause. Or a thumbs up or an LOL once you have your notes open. Let's see what we got. Awesome. Aqua, thank you, Julian. Thank you, Nichelle. Looking good, looking good. Awesome. All right, make sure you get your notes open. Again, you don't need to do anything with it yet. Just have it open and ready to go. I am giving you the answers as we go through class. So I am giving you the answers. All right, so we're going to talk about gravity and how gravity and motion are related according to Newton's laws of motion. Today, we are opening up the 3B notes. So we are working on the 3B notes. That's today's assignment. So let's review really quickly mass versus weight. Remember that we talked about how mass and weight are similar, but they're not actually the same. So you have the same mass no matter where you are in the universe, because mass is the amount of stuff or matter that you're made up of. And whether you're on Earth or floating in the middle of space, are you always made up of the same amount of stuff? Tell me in the chat box, are you always made up of the same amount of stuff? Yes, absolutely. So you are always made up of the same amount of stuff, so you always have the same mass, right? So if you have a mass of 56 kilograms, you will always have a mass of 56 kilograms. Now, weight, on the other hand, also called force due to gravity, it actually changes based on the acceleration due to gravity, because remember, forces are based on acceleration. So wherever you are, whether Earth or Moon or outer space, the amount of gravity matters for your weight. That's why you weigh more on Earth and you weigh less on the moon, and you are weightless in outer space where there is no gravity. But again, even though your mass stays the same, your weight changes based on gravity. So how heavy you feel changes based on gravity. Give me a thumbs up, everyone, if you understand that. Thumbs up if that is making sense. Yes, you would lose mass if you stopped eating, which might happen if you somehow ended up in outer space just floating. But in general, that wouldn't be an immediate effect, right? And that would be a result of right, physical weight loss, not a relationship with gravity. All right, so let's go ahead and use your pulling tools. Where did I get your pulling tools? All right, and I want to know, what does weight require? What things are accounted for in weight? Is it only mass? Is it only gravity? Is it both mass and gravity, or neither mass and gravity? Use your pulling tools. That is your fourth button at the top, of your participants panel. All right, I see some people saying mass. Again, think about what we just talked about. Are weight and mass the same thing? Are weight and mass the same thing? Think about that, and then let's keep on answering. Awesome, I've got about 12 answers. Oh, yep, there's a whole bunch of them pouring in. Loving it. All right, let me go ahead, publish these on the board, clear these out. And it looks like most of us are saying letter C, and letter C is actually correct, because remember, weight is not just mass. Weight actually includes the effect of gravity on that mass, right? So weight is actually both mass and the force due to gravity combined together. All right, smiley faces if you're beginning to understand that a little bit better. Smiley, smiley, smileys. Excellent. All right, this is actually the answer to number 1 in your notes. Remember that the answers in your notes are scrambled, so make sure you read carefully. Go ahead, take 30 seconds to answer this in your notes, and give me a green check when you have taken a picture or you have answered it in number 1. Go. All right, still need some green checks. Elena, Alejandra, Antonio, Chris, David, Aqua, Estella, Jelly, Jorge, Rob, and Thomas, green checks for number 1. Again, weight includes both mass and gravity. It's the effect of gravity on mass. All right, so let's go ahead and review Newton's first law of motion. All right, so let's do this together. Tell me in the chat box, an object at rest will what? Go tell me in the chat box. What's this word? Starts with an S. Will blank at blank. So an object at rest will, yes, Julian, it will stay. Yes, stay at what? An object at rest will stay at what? Yes, it will stay at rest, right? That's actually up on the board. That should be pretty easy for us, right? A body at rest wants to stay at rest just like you want to stay in bed. Objects will do the same thing. And an object in motion will what? Tell me in the chat box. Will what? In what? Yes, Vanessa. Yes, Julian. Yes, it will stay in what? It will stay in what? Yes, it will stay in motion. Exactly, Hannah. Exactly, Kimberly. It will stay in motion. And it will do this with constant what? Remember, what's that word that includes both speed and direction? Speed and direction. So how fast it's going as well as the direction in which it's going. Yes, it starts with the V, seeing lots of answers with the same velocity, right? So it will continue moving in the same direction forever and with the same speed forever, just like in outer space, unless it is acted upon by a what force? Another word for outside. A what force? What's another word for outside of it? Yes, an external force. All right, thumbs up, guys, if you remember this, if this is familiar. Hopefully this is looking good. So if it's at rest, it's going to stay at rest forever. If it's in motion, it's going to stay in motion forever unless somehow there's an external force working on it. Now, Newton's first law says, we just talked about that. Now let's relate that to projectile motion. So projectile motion is what happens when you throw an object on the earth. So on the earth, do objects stay in motion forever when you throw them? Tell me in the chat box. On the earth, do objects stay in motion forever when you throw them? No, what do they do? When you throw an object, it doesn't just keep on going straight forever and forever. What happens instead? It slows down and then what? Well, why does it stop though? Yeah, it drops, right? It falls to the ground and then stops once it hits the ground, right? So in projectile motion, the external force that's actually affecting this, because obviously there must be an external force since it's not staying in motion forever. What must that external force be? Tell me in the chat box. What must that external force be that must be acting on that? Starts with a G. The external force is what? Got an answer. Yes, Vanessa. Yes, Julian. Yes, it is gravity. All right, so in projectile motion, the reason your object does not keep on moving forever when you throw it is because there's actually gravity, and gravity is an external force, right? So this is going to change the velocity. This is going to change the speed and the direction. All right, this is number 2 in your notes. Give me a green check when you have it saved. Fill in the blank with the word external. You have 30 seconds. Go. All right, waiting on green checks. Alejandra, Antonio, Ari, Estella, Jelly, Jackie, Janice, Jorge, Rob, Shelby. Green checks, please. Again, we're in our notes. We are answering number 2 together. Perfect. All right, so let me go ahead and I am going to actually share this with you. I'm going to go ahead and show you exactly what projectile motion looks like. All right, so let me go ahead and point this out to you. All right, thumbs up, everyone, if you can see my screen here. Once you can see my screen, give it a moment to load and then give me a thumbs up once you can see it. I'll turn off my video so that it loads better. Perfect. Okay, so take a look here. We have a cannonball, a cannon with a cannonball. The cannon is raised, all right, and we can see that it has diameter, it has mass. I'm going to actually turn off air resistance. We're going to ignore air resistance right now. It's moving at 20 meters per second initially as it gets shot out of the cannon, okay, and I'm going to show it to you both normal and then slow. Okay, so let me go ahead and show it to you normal. All right, so you can see that right there. And again, did this cannonball continue in a straight line forever? Tell me in the chat box. Did this cannonball continue in a straight line forever? No. So clearly, again, there's something that is working on this cannonball. There is an external force changing its motion. So let's go ahead and slow it down. All right, and I'm going to go ahead and shoot it again. All right, and let's take a look at this. All right, so what you can see is that your horizontal motion is staying at this 20 meters per second, but your vertical motion is actually increasing due to the force of what? The vertical velocity towards the ground is increasing due to the force of what? What is this force? Fg. Again, that's the force due to what? Yes, it is the force due to gravity. So as this moves, you can see that the force due to gravity is pulling it down faster and faster and faster and faster until it hits the ground. Smiley faces if that's beginning to make sense. So projectile motion is the result of gravity beginning to pull it down. Beginning to pull it down. All right, so let's go ahead and actually break these components down, okay? So without gravity, this object would just continue moving in a straight line horizontally forever, right? That's Newton's first law. It would continue traveling forever. Gravity by itself pulls a ball straight down. That's the vertical motion, right? So by itself, if you just drop a ball, it's going to go straight down and get faster and faster because gravity causes it to accelerate, which means it gets faster. Smiley faces if this part makes sense. So horizontally, without gravity, it would move forever. With just gravity, it gets faster and faster as it hits to the before it hits the ground. Cool. Now, what actually happens though, what we saw is the actual motion of this cannonball is actually kind of this curved downward path. And this curved is what's called a projectile path, all right, or a parabolic trajectories. That's the shape in math, all right? So it's this curve that kind of gets bigger and bigger here, all right? So what we're trying to think of is, why does this curve happen? So if we were to break it down, what you can actually see is that you are actually combining both the horizontal path and the vertical path together to create this curve, create the actual motion. So what's really happening is horizontal velocity actually stays the same because, again, Newton's first law says once it's in motion, it's going to stay in motion. So horizontally, it stays with the same motion. Give me a thumbs up if that makes sense. All right, so it keeps on going straight to the side, but at the same time, it's also being affected vertically. And again, that vertical motion is actually getting faster and faster due to the external force of gravity. And as it gets faster and faster, it actually makes it curve downward more and more. So overall, the overall velocity is getting faster. So we can see this here. Again, the horizontal velocity stays the same. The vertical velocity is getting faster and faster, and overall we see this really cool curve that we call projectile motion. And this happens with every object that you throw on Earth, okay? All right, so Newton's second law, again, we're going through all of them and seeing how it relates to gravity. Newton's second law says that there is a relationship between an object's mass, its acceleration, and its force, okay? And remember, there's an equation for this. Do you guys remember what that equation is? Or you can look up here on the picture really quickly. What's the equation for Newton's second law? The most famous physics equation. Tell me in the chat box. F equals what? F equals what? Yes, F equals ma. Force equals mass times acceleration. Perfect. So what this means is that when we talk about gravity, gravity is in fact a force, and so therefore F equals ma also applies to gravity. It's just with the word gravity. So the force due to gravity equals mass times the acceleration due to gravity. All right, go ahead, give me a LOL face if that makes sense. LOL face if that makes sense. Okay, force due to gravity equals mass times acceleration due to gravity. It's still F equals ma, it's just with gravity, okay? So thinking about this, this means that all objects in free fall, all right, meaning you just drop them, you don't throw them, you don't do anything, you just drop them. All objects in free fall are actually only influenced by the force of gravity, and so all objects accelerate at 9.8 meters per second squared. So that means that all objects speed up at the same rate. Right, so what this means, right, all objects speed up at the same rate, okay? So in theory, what this means is that 1,000 kilogram mass and a 1 kilogram mass should actually hit the ground at the same time. So even though one weighs more, so even though the 1,000 kilogram mass weighs more because force due to gravity or weight, right, force due to gravity is also called weight, is affected when there's more mass, the acceleration or how fast it moves to hit the ground should not be affected, okay? So what's amazing is this is called Galileo's Leaning Tower of Pisa experiment. When he dropped both a large mass and a small mass at the same time, they actually hit the ground at the same time. All right, give me a thumbs up if that makes sense. You see this picture here? This is the Leaning Tower of Pisa. How many of you have heard of that experiment? Okay, good. So this is really, really cool, and we're going to see this in a moment. The problem is, though, think back to our question that we started off with in class. Do bowling balls and feathers actually hit the ground at the same time? One has a lot of mass, one has very little mass. Do they hit the ground at the same time? No. And why do you think that they don't hit the ground at the same time? What do you think is causing feathers to not actually hit at the same time, even though they should, according to this idea? Even though they should. Yes, there's actually another force in action. So it's actually not just the force of gravity. And so for feathers, it's not just free fall. For feathers, there's actually air that's resisting the motion of gravity. So it's actually air resistance working against the feathers, slowing them down. But think about what happens once we get rid of air. So let me go ahead. I am going to share this video with you up on the board. And it's a really cool video, so let me go ahead and grab this. And I want you to take observations and start typing them into the chat box, all right? So I'm turning off my video, and sharing this with you on the board. I'll put it in the chat box as well.
A heavy object and a light one, and drop them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant.
Looking good. All right, so at the beginning, when there was still air, tell me what happened in the chat box. Tell me your observation. What happened in the beginning of the video? They dropped the bowling ball and the feather at the same time. You can pause it, Antonio. You have control over it. What happened at the beginning of the video? Tell me in the chat box. Yeah, so when there was still air in there, there's resistance, right? So we saw what hit the ground first, right? Nichelle, you're saying the bowling ball hit first. What floated down? Let's be a little bit more specific than just saying it so that everybody knows what we're talking about. Yeah, so air resistance called the bowling ball to hit first. And then yes, the feathers stayed falling. The feathers kind of floated because they were being blocked by the air. There were molecules that we can't see, but there are actually molecules there that were blocking the feathers from falling down. Smiley faces if that makes sense. At the beginning of the video, right, bowling ball hit first, which it makes sense. That's what we think. Yes, but now then what they did is they took away all of the air and therefore all of the air resistance. So air resistance was no longer a resisting force in the chamber. So if there was no longer that resisting force, they're both only affected by gravity. Sure, I can take it off now that everyone's seen it. So tell me what happened when they were both only affected by gravity and no air? What happened when we got rid of air and the only force was gravity? Yes, they actually landed at the same speed, or at the same time. They sped up the same amount. They accelerated at the same rate. And so they hit the ground at the same time. Did mass matter when there was no air resistance? Did the mass matter at all? Did it have any effect, whether it was a heavy or light object? No. So in reality, when there's no air resistance, the actual weight of the object doesn't matter with which one hits first. They will actually hit the ground at the same time. All right, this is number 3 in your notes. Give me a green check when you have this saved. You have 30 seconds to fill in the blank with the word gravity. Go, just the word gravity. Julian, so I think what I'll probably do is I'll probably start adding everybody to them just as an optional thing so that anyone who wants to can jump in. Does that work? I don't really want to clutter people's schedules, but I think it would be more helpful than trying to figure out who wants to come versus who doesn't. And it says optional anyways on your schedule, so that way you know you can come whether you want to. Okay, cool. All right, Alejandra, Alicia, Chris, David, Aqua, green checks please, Jelly, Jorge, Julian, Landon, Rob, and Thomas, green checks for number 3, filling it in with the word gravity. Fill in the blank with the word gravity. All right, let's move on. Okay, so let's go ahead. Let's do some really quick checks here. All right, what is the acceleration due to Earth's gravity on a 10-kilogram object? Do you guys remember what's the acceleration due to gravity? What is the acceleration due to gravity? Right, we talked about it on the previous slide. What's the acceleration due to gravity on a 10-kilogram object? Go ahead, use your polling tools or tell me in the chat box, what is the acceleration due to gravity on a 10-kilogram object? Yes, exactly. The acceleration due to gravity on a 10-kilogram object is 9.8 meters per second squared, because that's the acceleration due to gravity in general. Now, what is the acceleration due to gravity on a 1,000-kilogram object? Got about 4 of you. Keep going, work together. You can see your classmates' answers. Think about, do you think they're correct? Do you think they're incorrect? All right, I do see most of you are saying letter B again, and that is correct. No matter what, the acceleration due to gravity on Earth is due to the Earth, right? So the acceleration due to gravity on a 10-kilogram or a 1,000-kilogram object is actually identical, the same acceleration. So this means that they speed up the same amount. So if they speed up the same amount based only on acceleration due to gravity in free fall with no air resistance, which object should hit the ground first? If there's only this identical acceleration due to gravity, no other things, which one hits the ground first? Same acceleration, same rate of speeding up. Which one hits the ground first? A, 10 kilogram, B, 1,000 kilogram, C, they hit at the same time, or D, neither hits the ground. Yes, yes, yes. Awesome. Looks like all of us are saying letter C, and that is correct because the only thing that's affecting them is just gravity and acceleration due to gravity. The only thing that affects them, that means that they are going to hit at the same time. Their mass and their weight does not matter. All right, give me a smiley face one more time if that makes sense. In this case, mass and weight do not matter in free fall. All right, this is the answer to number 4. Give me a green check when you have that saved. You have 30 seconds to choose they hit at the same time. Make sure, remember they are scrambled, so read carefully. Go. Green checks, please. Elena, Alejandra, Alicia, Ari, Brandon, Chris, David M, sorry. Estella, Jelly, Jorge, Taja, Rob, Shelby, green checks. Again, number 4 is they hit at the same time. Make sure you choose the correct answer because yours may be scrambled. Let's keep going. All right, the last of Newton's 3 laws of motion are that for every action, there's an equal and opposite reaction to the direction of the force. That means forces come in equal, opposite, and parallel force pairs. So that means if I am in outer space and I push a rock forwards, what way does my body move? Tell me in the chat box. If I am in outer space floating with my rock, I throw the rock forwards, what should actually happen to my body? What should actually happen to my body? Yes, my body will actually begin to move the opposite parallel direction. David, your dog is attacking you, which means I would go backwards. This actually happens when you're in a rolling chair. If you push forwards on your desk, your chair actually moves backwards. So there are equal and opposite forces. No matter what's happening, there's always equal and opposite forces. Now, what this means is that gravitational traction between two objects demonstrates this law. So the gravity of the Earth pulling on the moon is actually equal, exactly identical in amount, but opposite to the force of the moon on the Earth. Okay, so they both are pulling each other with the same force of gravity on each other. So the Earth pulls on the moon, but the moon also pulls equally on the Earth. And one of the most important things that happens here is this actually causes the ocean tides because it's pulling water towards itself. The moon is pulling water on the Earth towards itself, which causes ocean tides, causes waves, causes the tides to rise and to fall. Smiley faces if that's beginning to make sense. So the force due to gravity on Earth by the moon versus the force due to gravity on the moon by the Earth are identical, but opposite. Identical amounts, but opposite. Now this should make sense because if either force was larger, then that object would actually begin to accelerate towards the center, right? So if we take a look here, okay, and I have an object on the end of a rope, and I begin to spin it, right? At no point is this object beginning to accelerate towards my hand? Because neither one has a stronger force and therefore more acceleration towards the center. Smiley faces if that makes sense. Smiley faces if that makes sense. All right, so if my hand is Earth and the object is the moon, the metal is the moon, all right, they're not moving towards each other. So they have equal and opposite forces, okay? However, what you're probably thinking is if they have equal and opposite forces, right, how is it that the moon can be pulling on the Earth just as strongly, but the Earth is not rotating around the moon's actually rotating around the Earth, all right? Go ahead, give that a moment. Does that make sense? Does that question, do you understand why that question would be confusing? Yes, no? If you're like, if they're equal and opposite, why is the moon revolving around the Earth and not the other way around? All right, give me a smiley face if that question makes sense. That should boggle your mind. You should be like, what? That's right. What? All right, so here we go. This is the reason. Even though the forces are equal and opposite, remember that acceleration is actually inversely related to mass. So that means that because the Earth is much larger than the moon, okay, the Earth actually therefore has a smaller acceleration. All right, so that means that in reality, the Earth and moon are actually rotating around each other. All right, it's just that the Earth is so much bigger that you can't tell that the Earth is being caused, that the moon is causing the Earth to rotate. So the Earth has a larger mass and therefore has a much smaller acceleration, whereas the moon has a smaller mass and therefore a much larger acceleration, which is why the moon has a much bigger circle around the Earth. Okay, so again, if you take a look at this, all right, so my hand is much larger, but do you see that my hand is actually wobbling to cause this to move around? Do you guys see how oops, just hit my head. Do you guys see how my hand is actually wobbling to keep the moon moving around it? If my hand is the Earth, tell me in the chat box, do you see my hand moving back and forth? It's wobbling very slightly. Yes, so that's actually true with the Earth as well. The Earth actually wobbles, and it wobbles around this point called the barycenter. So the moon and Earth actually do orbit each other, but they orbit each other around the barycenter, and the barycenter is actually closer to the larger mass. And in this case, the Earth is so much more massive, so much larger, that the barycenter is actually inside the Earth. So the Earth wobbles in this tiny circle that we can't see, and that's why it's not orbiting around the moon necessarily, but it's actually wobbling. But still, the moon is affecting the Earth just as much as the Earth is affecting the moon. All right, give me one more time a smiley face if that's beginning to make sense. That should blow your mind, guys. It's amazing. All right, so fill in the blank for number 5 with the word inversely. I don't know. It would depend on why. There are different reasons why that might happen, Julian. All right, so the number 5 is inversely. Acceleration and mass are inversely related. And then number 6, fill in the blank with the word barycenter. All right, so go ahead, I'm going to give you 1 minute to answer that. 45 seconds. 45 seconds to answer both of those. Give me green checks when you have them both saved. All right, green checks. Elena, Alejandra, Alicia, Antonio, Ari, Chris, Estella, Jelly, Julian. Thank you, Julian. Awesome, thank you. Waiting on Rob, Shelby. Looking good. All right, everyone. So at this point, we should be able to understand mass versus weight, right? We reviewed that. We should be able to understand how projectile motion is affected by Newton's first law, how objects in free fall are affected by Newton's second law, F equals ma, and how Earth and Moon are affected by gravity due to Newton's third law, equal and opposite forces that are parallel to each other. All right, so go ahead on the whiteboard, put your sticker up there. Tell me, how are you feeling about today's objectives? Use your pointer tool. It's the second tool. And then go ahead, point. Are you on the very confused side? Need help? Pretty good. Awesome. How are we feeling? David, that's sometimes how I feel about my daughter. I'm like trying to work and she's like literally climbing up me like I'm a jungle gym. I'm like, please get off of me. Looking good. All right. I'm glad we're feeling pretty good. Some of us are feeling awesome. I love it. If you're ever on this side, don't be shy. Come to support session and I can help you with anything that you're confused about. All right. Always think to yourself, what's one thing that you learned or reviewed today so that you can begin to solidify that in your mind. So be intentional. Think about, what have I learned today? All right. So at this point, I'm going to go ahead and stop the recording. Make sure you submit your notes and then I am going to give you the end of class word. Here we go. Recording.